A standard deck of cards has 52 cards in 4 suits. I've shown that here, although I just noticed some interesting detail about this graphic that I've chosen and shown to you before. The ace strangely has a T. I don't know, maybe there's a foreign language where ace starts with, the word for ace starts with T. I'm not sure, but in any case, these are the aces. We've got 2s, 3s, 4s, all the way up to 10, and then 3 face cards, the jack, the queen, and the king, in each of 4 suits. I don't assume that everyone is familiar with cards, which is why I show this graphic from time to time when you might need it. What is the probability of drawing a random card from this standard deck of cards and selecting a single-digit composite number or a club? So the single-digit composite numbers, it's almost like the opposite of prime. We learned this earlier this year. Prime numbers have only 2 factors, 1 and the number itself, which is why 1 is not prime, because 1 has only 1 factor. 0 is not prime, because 0 has every number as a factor, because 0 multiplied by anything is 0. But you get past 0 and 1, and you start looking at the counting numbers past 0 and 1, and it's easy to identify the primes, because the primes have only 2 factors. The only way to get 2 is 1 multiplied by 2, same for 3, 1 multiplied by 3. But 4 you could do 2 times 2 or 1 times 4. And so the composite numbers have more than 2 factors, and the composite numbers would be the 4s. I almost circled 5. 4, 6, 8, 4, 6, 8, and 9 certainly, because 3 times 3. And I almost circled 10 because, of course, 10 is composite, but if I read carefully, it says single-digit composite. So the 4s, the 6s, the 8s, the 9s in each suit. So when we start to consider the probability of getting a single-digit composite number, I'll represent that this way: probability of a single-digit composite number. There are 4 in each suit, and there are 4 suits, so 16 of the 52 cards are single-digit composite numbers. But that's not the only favorable outcome. We also have a favorable outcome if we draw a club, and all of these are clubs, and so the probability of a club is 13 out of 52. Since a single-digit composite number is a favorable outcome or a club is a favorable outcome, I would add these probabilities. Now, that statement could have caused some confusion right there, because we've been practicing multiplying probabilities. But we multiply probabilities when we're talking about events that occur one after another, multiple events. This is a single event. I'm going to draw 1 card, and I win if it's a single-digit composite number or if it's a club. And so in that case, it would make sense to add those probabilities because there are more favorable outcomes. Every single-digit composite number is a favorable outcome, and every club is a favorable outcome. But this sum, 29/52, is not the correct probability. And I'm going to ask you to pause and see if you can think about why, what mistake has been made here, or what have we overlooked. When I say pause, I assume you hit the pause button, but if not, you should do that and think about that question. If I show all of the single-digit composite numbers and all of the clubs in a Venn diagram, the 4 of clubs, the 6 of clubs, the 8 of clubs, and the 9 of clubs will all be placed in the intersection, because those are single-digit composite numbers and they're clubs. The other single-digit composite numbers would be the 4, 6, 8, and 9 of the other 3 suits, hearts, diamonds, and spades. And the rest of the clubs would be in the clubs only section of this Venn diagram. But by adding these 2 probabilities, these 2 individual probabilities, we have double counted these clubs, these single-digit composite clubs. We've double counted them as favorable outcomes twice. And so in a situation like this, you need to subtract the 4/52, which is the probability of single-digit composite and club. It's for the same reason that which would, I should finish this thought, sorry, which would give us the final probability of 2550 seconds. Had a little slight dyslexic moment there, sorry. 2550 seconds. Now let me glance at my, yeah, that's correct. Okay, this is not a brand new idea for us. Although last time we looked at this idea, actually last time we looked at this idea was in the recent homework where you had the photos of Nikki, a photo album with photos of Luke, photos of Nikki, and photos of Luke and Nikki. In order to calculate the correct number of total photos, you had to recognize that the photos that contained Luke and Nikki counted for both twins, and so you didn't double count them, and you correctly got 40. The same thing works with probability. Well, we already talked about how it applies to probability, but let me talk about how it applies to area. If I was finding the area of this, let me define this better. If I was trying to calculate the area of this black region, I wouldn't want to count this yellow area and this. I could add the yellow area and the blue area, but then I would need to subtract out this intersection because I've double counted it. That's something we looked at in some geometry problems. So when you have intersecting sets, you have to subtract out the overlap, and that's all we're doing just in terms of probability. So that sort of explains this concept of compound probability, where you have favorable outcomes that overlap, and you'll have lots of opportunity to practice it in the upcoming problems. If you see a slide, a draw it slide with no explanation, try the problem and then either solve it and then go to the next slide to watch the short video to confirm your solution, or if you're stuck and not sure how to start, then go to the next slide and watch the video to start to understand how to do it. Maybe try the next one on your own, or go back and solve that one on your own. Use the Nearpod in the way that best helps you learn this concept. There is no learning opportunity that will be graded, but this is your math work for today, so use this Nearpod well, and consider joining the 1:30 p.m. Zoom for extra instruction on this.